Hello everybody, this is Mr. Parker from parkermaths.com, and today we're going to be looking at the OCR Mechanics 1 paper from June 2008. You can download a copy of the question paper by clicking here. If you've already had a go at it and you want to mark it quickly, you can download the mark scheme over here as well. Both of those links go directly to the OCR website. If you've watched one of these videos before, you might want to skip ahead to question 1 using this link here. Before you watch this video, I strongly recommend that you've attempted the paper, preferably under exam conditions, so you've figured out which questions you already know how to do and which ones you need a little bit of help on. When I get onto the first question, there'll be a list of links down the side here to all the individual questions, so you can skip ahead and have a look at any of the questions that you think you particularly need to work on. You might find, if you're already confident with a question, that you want to watch it at double speed to speed things up. There's a cog at the bottom of the YouTube window on most modern browsers which allows you to do that. Remember, you can also pause it and watch bits again if you don't fully understand something the first time around. And if you want to look for a different past paper, feel free to check out parkermaths.com for all the other A-level revision resources we've got down here. Okay, let's get started. Question 1. A car of mass 900 kilograms is travelling in a straight line on a horizontal road. The driving force acting on the car is 600 newtons, and a resisting force of 240 newtons opposes the motion. In part 1, we have to show the acceleration of the car is 0.4 meters per second squared. Let's start by drawing a diagram. So here's the car, and it's got a mass of 900 kilograms. And we have a driving force of 600 newtons, so we'll do that in a forwards direction. And we have a resisting force of 240 newtons in the opposite direction. So let's write down a force equation. So on the left hand side we're going to have net force. So let's take right to be positive, and we have 600 newtons to the right minus 240 newtons in the opposite direction equals mass times acceleration. So 900 is the mass multiplied by the acceleration a. All we've got to do to find a is divide through by the 900. So let's work out this bit in our head while we're going. That becomes 360 divided by 900, and if you cancel this fraction down you get 4 out of 10, which is the same as 0.4 meters per second squared. You don't have to do that in your head, you could put it into your calculator, you'd still get the same answer. In part 2, we need to calculate the time and the distance required for the speed of the car to increase from 5 meters per second to 9 meters per second. So we'll start by writing down our values for SUVAT. Displacement's unknown. The initial velocity is 5 meters per second. The final velocity is 9 meters per second. The acceleration is 0.4 meters per second squared. We found that in part 1. And the time is also unknown. Let's start by finding the time. To do that we need an equation involving u, v, a and t. The equation we want is v equals u plus at. V is 9, u is 5 and a is 0.4. So let's take away 5 from both sides and we get 4 equals 0.4 t. To get t on its own we divide through by 0.4, and 0.4 goes into 4 10 times, so t must be 10 seconds. Again, you could check that with your calculator if you needed to. We also need to find the distance required, which in this case is the same as the displacement, so we need a formula that involves s. The one I'm going to use is s equals half u plus v t, because remember, now that we've done this we know what t is, so we could write this into our SUVAT over here as 10 seconds. We could have used v squared equals u squared plus 2as, but this one is easier to get our answer out from. So we've got half of 5 plus 9 multiplied by 10. A half times 10 is 5, multiply that by 14 and we get 70 meters. Question 2. Two horizontal forces act at the point O. One force has magnitude 12 newtons and acts along a bearing of 0, 0, 0. The other force has a magnitude of 14 newtons and acts along a bearing of 0, 3, 0. So all that's shown in the diagram. We need to show that the resultant of the two forces has a magnitude 25.1 newtons, correct to three significant figures. The first thing I'm going to do is turn this diagram here into a force triangle. I'm going to draw the 12 Newton force going upwards, and where the 12 Newton force vector ends, I'm going to draw the 14 Newton force. I've got this angle 30 degrees to put on my diagram as well, and the way I'm going to figure out where that goes is by using the fact that the angle in between the 12 Newton force and the 14 Newton force is 30 degrees. So if I extended my 12 Newton force and I've got my 14 Newton force here, that means this must be the angle that's 30 degrees. I'm now going to draw on my resultant force, which will go from the beginning of the 12 Newton vector to the end of the 14 Newton vector. So I'll label that R. In order to work out the length of R, we've got a triangle here, but we need to know one of the angles inside the triangle. The easiest one to work out will be this one here, because we have a straight line with one of the angles as 30, so the other must be 150 degrees. Now I'm going to use the cosine rule, which is given in the formula book, and the cosine rule says that a squared equals b squared plus c squared minus 2bc cos a. So I'm going to choose my a here to be the resultant force. So I'm going to write r squared equals the other two sides squared, so 12 squared plus 14 squared minus 2 times 12 times 14. The angle A has got to be opposite the side A, so that's the 150 here, so cos 150 degrees. So I'll put that into my calculator. I get 12 squared plus 14 squared minus 2 times 12 times 14 cosine 150, and I get 630.98. I need to find R, so all I've got to do is square root my answer, and I get 25.1 as I expected. In part 2, I need to find the bearing of the line of action of the resultant. All that's asking me to do is find the angle between the resultant force and north, which is shown here on the diagram. So I'm trying to find this angle in here, which I'll label as theta. To do this, I'm going to use the sine rule, which says sine A over A equals sine B over B. So I'm going to choose theta to be A, so I'm going to get sine theta over the opposite side, which in this case is the 14, equals the only other angle I know in the triangle is the 150, so sine 150 divided by the opposite side, which in this case is R, which is 25.1. Although when I do this calculation, I'm going to use the answer button on my calculator, so I've got the exact value for this part. Let's multiply both sides by 14. I get sine theta equals 14 sine 150 divided by 25.1. So to get theta, I need to use inverse sine of everything on the right hand side. And I'll put that into my calculator. So I get inverse sine of 14 sine 150 divided by my answer from the previous part, which is 25.1, and if I do that I get 16.2 degrees to three significant figures. Remember, I need to write my answer as a bearing, so I'm going to change that to 016.2 degrees. You don't actually lose marks in this question for not displaying your answer as a bearing, but we should really, because that's what the question asks. Question 3. An athlete runs in a straight line from point A to point B and back to point A. The diagram shows the velocity time graph for the motion of the athlete. The graph consists of 3 straight line segments. In part 1, we need to calculate the initial acceleration of the athlete. Well, for any straight line segment in this graph, acceleration is the change in velocity divided by the change in time. So this is our initial stage from 0 to 5. So the change in velocity, he goes from 0 to 6. So that's going to be 6. The change in time is over 5 seconds. So we need to calculate 6 over 5. And that's going to be 1.2 meters per second squared. In part 2, we need to calculate the total distance the athlete runs. In order to do that, we just need to work out the area under the graph. So I'm going to call these two regions A and B. You don't need to label these on your diagram, these are just to help me talk about them. So region A is a triangle. So we can say that S equals base times height divided by 2. The base is 10, the height is 6, so I would do 10 times 6 over 2. I'm going to get another area here that is also 10 times 6 over 2. Both of these are the same. If I'd have been asked to figure out the displacement, this would have been different, because this area here I would have done 10 times minus 6 and this area would have been negative. But when I'm working out the total distance from a graph, I'm only interested in the actual areas and not the sign of the areas. So 10 times 6 is 60, divided by 2 is 30, plus another 30, that is going to be 60 meters. In part 3, I need to calculate the velocity of the athlete when t equals 17. To answer this question, we need to consider which segment of the graph we're interested in, and at t equals 17 we're on this straight line segment here. So I'm going to write down SUVAT for the bit just between 15 and 20. So SUVAT. Displacement is unknown, although we could work it out in this little bit here. The initial velocity is minus 6. The final velocity is what we're trying to find. It's going to be somewhere around here, but we don't know exactly what it will be yet. So we'll put a question mark for that. The acceleration we don't yet know, and the time is going to be at 17 seconds, but we're not going to use 17 because we're starting at 15. So to get from 15 to 17, that's 2 seconds, so the time is going to be 2 seconds. We can work out this value of acceleration in a similar way to what we did for part 1. We can say that the acceleration is the change in velocity divided by the change in time. This time our velocity goes from minus 6 to 0, which is a change of positive 6. The time is 5 seconds because we're going from 15 to 20 for this whole segment here. So divided by 5, it's still 1.2 meters per second squared like in part 1. Now that we know the acceleration, let's write that into our SUVAT over here. We know U, A, T, and we're trying to find V. The equation we want to use is V equals U plus AT. We don't know V, but we do know U is minus 6, and we're going to add 1.2 lots of 2. Well, 1.2 times 2, that's 2.4. If we add that to minus 6, we get minus 3.6 meters per second. Question 4. A particle P of weight 30 newtons rests on a horizontal plane. P is attached to 2 light strings making angles of 30 degrees and 50 degrees with the upward vertical, as shown in the diagram. The tension in each string is 15 newtons and the particle is in limiting equilibrium. And in part 1 we need to find the magnitude and direction of the frictional force on P. Let's start by adding these 15 Newton forces to the diagram. So both of these are 15 newtons. The direction of the frictional force has to oppose motion. If we think about these two forces, this force here is more in the horizontal direction than this force. So you would expect in the horizontal direction this force to have a larger magnitude than this one, which means our friction has to effectively help out this force here to keep everything in limiting equilibrium, and F lim is going to go to the left. To find out how large it is, we're going to write down a force equation for these three forces in the horizontal direction. So resolving horizontally, it's always a good idea to state which direction you're resolving in. The component of this 15 Newton force here in the horizontal direction is going to be 15 sine 50. The component of this 15 Newton force is going to be 15 sine 30, but it's in the opposite direction, so we'll put minus 15 sine 30. The friction's also in the negative direction, so we'll put minus F lim. And all of that is going to equal 0 because it's in limiting equilibrium. If we rearrange to get F lim on its own by adding F lim to both sides, we'll get limiting friction is equal to 15 sine 50 minus 15 sine 30. Let's put that into our calculator. 15 sine 50 minus 15 sine 30 gives us 3.99 newtons to three significant figures. In part 2, we need to find the coefficient of friction between P and the plane. In order to find the coefficient of friction, we're going to need to think about the normal contact force. So I'm going to add the vertical forces to my diagram now. I've got a weight force going downwards, which is given in the question as 30 newtons. That means I'm going to have a normal contact force in the opposite direction upwards, which I will call R. So to find this normal contact force, we are going to resolve vertically. So let's think about all the forces that will have a component in the vertical direction. We're going to have a component of this 15 Newton force, a component of the other 15 Newton force. We're going to have R, and we're going to have 30 newtons in the other direction. Let's take upwards to be positive, and we'll say we've got R plus 15 cosine 30 for the force on the left. We're going to have 15 cosine 50 for the other 15 Newton force. And in the opposite direction, we've got 30 newtons. The particle's in limiting equilibrium still, so it's going to equal 0. So to isolate R, we're going to have to add 30 to the other side and subtract these two forces. So we get 30 minus 15 cos 30 minus 15 cos 50. Let's use our calculator to work that out. 30 minus 15 cos 30 minus 15 cos 50 gives us 7.37 newtons to three significant figures. However, we're going to need this calculation later on in the question, so I'm going to use the answer value in my calculator for this to get a more accurate answer for the next part. We already know the limiting friction from the previous part of the question. However, this isn't the last calculation in my calculator, so I'm actually going to use this line of working here for F lim, because that will give me a more accurate answer than using the one I rounded to three significant figures. So remember, F lim is the coefficient of friction times the normal contact force. So that means that the coefficient of friction is going to be F lim divided by the normal contact force. So let's substitute some numbers in here, and I'm going to get 15 sine 50 minus 15 sine 30. That's just my limiting friction that I've got from up here, and I'm going to divide that by my normal contact force. I'm going to put 7.37, but I'm actually going to use the answer button on my calculator. So I'm going to get 15 sine 50 minus 15 sine 30, all divided by my answer from the last question, which gives me 0.542 to three significant figures. Question 5. A railway wagon A of mass 2,400 kilograms and moving with speed 5 meters per second collides with railway wagon B, which has mass 3,600 kilograms and is moving towards A with speed 3 meters per second. Immediately after the collision, the speeds of A and B are equal. Part 1 says, given that the two wagons are moving in the same direction after the collision, find their common speed. State which wagon has changed its direction of motion. Let's start off by drawing a diagram. So we're going to consider the situation before the collision and after the collision. So before the collision, we are going to have two separate particles. We're going to have wagon A, which has a mass of 2,400 kilograms and is moving with speed 5 meters per second. And we've got wagon B, which has mass 3,600 kilograms, and that is moving in the opposite direction with a speed of 3 meters per second. So we know all the information for the before situation. After the collision, the speeds of A and B are equal, and in this part in particular they're moving in the same direction, and if they've got equal speed in the same direction, we can consider them to be just one big particle. So the mass of this particle will be the sum of the two original masses, which in this case will be 6,000 kilograms. And we want to know the speed it's travelling at and which direction it's going at. I'm just going to create myself a little bit of space above here. If I want to know which direction it's travelling in, I just need to consider which particle here has the most momentum. So for this particle, we're going to do 5 times 2,400, that's like times in by 10 and half in it, and that's going to give us 12,000 kilogram meters per second. For particle B, I need to do 3 lots of 3,600, which gives me 10,800 kilogram meters per second. So because particle A has more momentum than particle B, it's going to end up travelling to the right. So the wagon that's going to change direction is wagon B. So I'll write that down to start with. Now let's go about calculating the velocity v of the whole thing afterwards. Remember, both particles move with the same velocity. So we're going to write down a change in momentum equation, and that says that momentum before the collision is going to be the same as the momentum after the collision. Let's take right to be the positive direction. So the momentum of A is going to be 5 times 2,400. We've already worked these out, but we'll write down the calculations to make it clear. The momentum of B is in the opposite direction, so we'll say that's negative, so minus 3 times 3,600. That's the momentum before the collision. The momentum after will be the combined mass, 6,000, multiplied by the velocity. So that's going to be 6,000 v. Remember, we already know which direction it's going in, it's moving to the right. So let's simplify this left hand side. We've already done most of the calculations. We've done 5 times 2,400 here, we've done 3 times 3,600 here. So if we do the difference between these two, we are going to get 1,200. And that's going to equal 6,000 v. So v is just going to be 1,200 divided by 6,000, which is going to give us 1/5 or 0.2 meters per second. So the speed of the wagon is 0.2 meters per second, and it's wagon B that changes direction. Question 5, part 2. Given instead that A and B are moving with equal speeds in opposite directions after the collision, calculate, in part A, the speed of the wagons. Well, I'm just going to borrow my diagram from part 1. So the diagram for before the collision is the same as in part 1. The diagram for after the collision will be different now, because we'll still have two particles. They won't combine for this part. So here's particle A, still has a mass of 2,400 kilograms, but they're going to be moving in opposite directions. So we'll say this one is moving to the left with a speed v, and we've got particle B with a mass of 3,600 kilograms, and that is moving to the right with the same speed v. Although it looks as though there are two things that we don't know in this diagram, they're actually represented by the same letter, so we only have one unknown in our momentum equation. So let's write down the momentum before the collision. That's going to be 2,400 multiplied by 5 minus 3,600 multiplied by 3. We've already worked that bit out in part 1. On the other side, particle A is now moving to the left, so we're going to say the momentum of particle A is minus 2,400 multiplied by v. Particle B is going to the right, so that will be positive, and that will be 3,600 v. Let's simplify this a bit. We know from earlier that this gives us 1,200. I can collect like terms together here. I can do 3,600v minus 2,400v and get 1,200v. Well, if 1,200 equals 1,200v, then clearly v has got to be 1 meter per second. In part B, we need to calculate the change in momentum of A as a result of the collision. Well, let's just think about particle A on its own. The momentum of A before the collision is 2,400 multiplied by 5, which gives us 12,000 kilogram meters per second. The momentum after the collision is given by our velocity times our mass. We now know this velocity is 1 meter per second. It's negative because it's going to the left, so we're going to have minus 2,400 multiplied by 1, which gives us minus 2,400 kilogram meters per second. So the change in momentum is going to be 12,000 minus 2,400, and that's going to give us 14,400 kilogram meters per second. Question 6. A model train travels along a straight track. At time t seconds after setting out from station A, the train has velocity v meters per second and displacement x meters from A. It is given for 0 is less than or equal to t is less than or equal to 7 that x equals 0.01 t to the power 4 minus 0.16 t cubed plus 0.72 t squared. After leaving A, the train comes to instantaneous rest at station B. In part 1, we need to express v in terms of t and verify that when t equals 2, the velocity of the train is 1.28 meters per second. In this question, we're not dealing with constant acceleration, so we can't use any of the normal equations of motion. However, we can use the definition of velocity, which is that it's the rate of change of displacement. So we can say that v equals dx by dt, which means that all we need to do to find the velocity is differentiate our expression for the displacement. So remember, to differentiate any polynomial, we multiply by the power and then we reduce the power by 1. So we're going to do 4 times 0.01, which is 0.04, and we're going to reduce the power to t cubed. In a similar way for the second term, we're going to multiply by 3 and then reduce the power by 1, and we get minus 0.48 t squared. Multiplying the third term by 2 gives us 1.44, and then reducing the power by 1 gives us just t. So this is our expression for v in terms of t, and next we need to substitute in t equals 2 to verify that we get a velocity of 1.28 meters per second. So when t equals 2, v is going to be 0.04 multiplied by 2 cubed minus 0.48 multiplied by 2 squared plus 1.44 multiplied by 2. We get 1.28. For part 2, we need to express the acceleration of the train in terms of t, and hence show that when the acceleration of the train is 0, t squared minus 8t plus 12 equals 0. Well, the definition of acceleration is that it's the rate of change of velocity, which is dv dt. So all we've got to do to find the acceleration is differentiate our expression for velocity. So remember, to differentiate any polynomial, multiply by the power and then reduce the power by 1. So we get 0.12 t squared minus 0.96 t. Reducing the power of t, we'll just get a constant, we'll just get plus 1.44. So this is our expression for acceleration. We're interested in when the acceleration of the train is 0, so when a equals 0, we're left with 0 equals 0.12 t squared minus 0.96 t plus 1.44. We've almost got the expression we started with. We've got a quadratic, but it's not got the same coefficients yet. To get them, all we need to do is divide by 0.12. If we do that, we get t squared here, because 0.12 divided by 0.12 is 1. How many 0.12s go into 0.96? That's the same as how many 12s go into 96, and that's 8, so we get minus 8t. How many 0.12s go into 1.44? That's going to be 12, so we get plus 12. So we get 0 equals t squared minus 8t plus 12 as required. In question 6 part 3, we need to calculate the minimum value of v. Let's borrow some of our answer from previous parts of the question. We have an expression for v, and in part 2 we also found that when a was 0, this expression was true. To calculate a minimum value of v, we need to differentiate v and then set it equal to 0. Well, if you differentiate v, you get a. So we've actually done that in a previous part of the question. All we need to do now is solve this equation. So we've got 0 equals t squared minus 8t plus 12, which will factorise. We're looking for two numbers that multiply to make positive 12 and add to make negative 8. Those two numbers are minus 2 and minus 6. That gives us two solutions, t equals 2 or t equals 6. However, one of these points will be a maxima and not a minima. We need to figure out which one is the minima, and we can do that quite easily by thinking about the rough shape of the graph. So we know it's a cubic equation, and the coefficient of t cubed is positive. That means our graph will go up, down, up. We can also figure out a point on the graph because every single term involves t. That tells us that if we substitute in t equals 0, we would get a velocity of 0. So our curve will go up, down, up. Now this curve isn't completely accurate, but it is enough to tell us which point will be the minima and which point will be the maxima. So because 2 comes before 6, we must know that the maxima is occurring at 2 and the minima is occurring at 6. So we can say this one is a max and this one is a minimum. So we're interested in the minimum at t equals 6. To find out what the value of v at that point is, we substitute it back into our original equation. So we're going to do v equals 0.04 multiplied by 6 cubed minus 0.48 multiplied by 6 squared plus 1.44 multiplied by 6. Let's put that into our calculator. And if we do that, we get V equals 0. In question 6 part 4, we need to sketch the velocity time graph for the train and state the direction of motion of the train when it leaves B. Let's draw ourselves some axes ready. And we're going to need to borrow some information from earlier in the question in order to sketch this graph. We know that it's going to be a cubic shaped graph because the highest power is t cubed. We also know from earlier in the question that a maxima occurs when t equals 2, and we know a minimum point occurs when t equals 6, and we also know that at that point v is 0. We worked that out in part 3. So this is enough information to sketch our curve. It's going to start at 0. It's going to have a cubic shape, and we know at t equals 6 it's going to be a minimum at 0. We also know that this point here is going to happen at t equals 2. So we've got a cubic shape, always positive, never crosses the axes, and at t equals 6 it should have the value of 0. So we've sketched the TV graph for the train. We now need to state the direction of motion of the train when it leaves B. Well, it would be useful to have these points A and B on the graph. If we go back a little bit, we can see the question again, and it says that after setting out from station A, so that must be at the beginning of the graph, and it says the train comes to instantaneous rest at B. Something is at instantaneous rest when its velocity is 0. So this is point B, this is point A. So when the train leaves a station, it must still be moving away from A because it has the same velocity and it's positive as when it left the station in the first place. So the direction is away from A. In part 5, we need to calculate the distance AB. We have this equation for our displacement, which we found earlier in the question, and if we look at the graph, you can tell that it never crosses the axis. That means there is never a point in which its velocity is back towards its start position. It's always positive or 0. That means for this question, displacement is effectively the same thing as distance, and all we need to do is find out what the displacement is at t equals 6 when it reaches B. So to answer this question, the only thing we need to do is substitute in t equals 6 into this equation. And we get 4.32 meters. Now, if you're sensible and you're checking your answer to see if it makes sense, 4.32 meters, don't forget that it's actually a model train and not a real train. So 4.32 meters between stations is actually quite reasonable. Question 7. Two particles P and Q are joined by a taut, light, inextensible string which is parallel to a line of greatest slope on an inclined plane on which the particles are initially held at rest. The string is 0.5 meters long and the plane is inclined at 45 degrees to the horizontal. P is below the level of Q and 3 meters from the foot of the plane. Each particle has mass 0.2 kilograms. Contact between P and the plane is smooth. The coefficient of friction between Q and the plane is 1. The particles are released from rest and begin to move down the plane. Part 1 wants us to show that the magnitude of the frictional force acting on Q is 1.386 newtons correct to 4 significant figures. Now there's a lot going on in this question, but most of it is actually already on the diagram. There's only a few things in here that we need to add ourselves. We already know the length of the string. We've already got on the diagram the 45 degrees. We already know P is below Q. Each particle has mass 0.2 kilograms. That's not shown on the diagram. So maybe we could put over here P equals 0.2 kilograms and Q equals 0.2 kilograms. Notice that P and Q have different coefficients of friction, and we need to be careful later on when we're working with that. And for part 1 we are only interested in what's happening to Q up here. Remember, Q is the one that has coefficient of friction 1. So for this part of the question, let's write down that mu equals 1, and I'm going to draw a diagram which isolates particle Q. So it's on a slope of 45 degrees. There is going to be a limiting friction which is opposing its motion down the slope, so we'll call that F lim. There is going to be a weight downwards which is going to be 0.2 multiplied by G, and we're also going to have a force pulling it down the slope from the other particle. So we're going to have a tension in the string down here. Now let's have a think about how we know there would be a tension in this string. Both of these particles have an equal force down the slope due to the weight. However, particle P doesn't have any friction acting on it. It's smooth. That means that particle P doesn't have any resistance from the slope to slow it down. We've got one more force we need to add on here, which is the normal contact force, R, and that's going to be at right angles to the slope. So we're interested in finding the frictional force, and to do that we need to first calculate this normal contact force. So we are going to resolve perpendicular to the slope. So let's take the direction of R to be positive out away from the slope here rather than into the slope, and we've got this force R. Tension and limiting friction are parallel to the slope, so we can ignore them. We've just got the component of the weight into the slope, so it's the opposite direction to the normal contact force, and that's going to be 0.2 G cosine 45 degrees. The particle's not accelerating into or out of the slope, so we can say that mass times acceleration is 0, so R is just going to be 0.2 G cos 45. And if we put that into our calculator, we get 1.3859 and so on. So to calculate limiting friction, we need to do the coefficient of friction multiplied by the normal contact force, which in this case means we're going to multiply 1 by the normal contact force that we've got here, which is going to give us 1.386 newtons to 4 significant figures as required. In 7 part 2 we need to show that the particles accelerate at 3.465 meters per second squared, correct to 4 significant figures. We also need to calculate the tension in the string. This time I'm going to draw my diagram of the whole system. The benefits to working with the whole system in one go are that you can ignore any internal forces. And to see what I mean by that, we'll go back to the previous diagram. In here, between the two forces, there will be a tension force. If we think about it acting on P, there will be a tension going up the slope, and there will also be a force acting on Q, which is a tension pulling it down the slope. If we're thinking about the whole system as one particle, these tension forces will cancel out with each other. Here's our diagram then. When we're thinking about the whole system, we can consider both particles as being just one big particle, so it will have a mass of 0.4 kilograms. Remember, there won't be any internal forces, so there's no tension force. Forces that we do have, we've got the weight downwards, which will be 0.4 G. And we've got limiting friction going up the slope, which we've already calculated. Remember, this friction is only acting on one of the particles, and it has a magnitude of 1.386 newtons to 4 significant figures. Although if we're actually going to use this in the calculation, we may as well use the exact calculation we used earlier. So let's resolve parallel to the slope. Now this limiting friction that's 1.386, we've got a more accurate calculation to get that, and that will be 0.2 G cos 45. So I'm going to write that next to it. 0.2 G cos 45. We should always use exact values when we've got them. So thinking about what's happening down the slope, we've got 0.4 G sine 45, that's the component of the weight. In the other direction, we've got 0.2 G cos 45. On the right hand side of the equation, we'll have mass times acceleration. In this case, that will be 0.4 A. So to work out acceleration, we're going to do 0.4 G sine 45 minus 0.2 G cos 45, and we're going to divide that all by 0.4. And as required, if you round the answer to 4 significant figures, you get 3.465. We also need to calculate the tension in the string. Now, we can't use the whole system to calculate the tension because, as we mentioned earlier, we can ignore the internal forces when we're considering the whole system. So I'm just going to consider one of the particles, and I'm going to consider, if we look back, particle P here. I'm going to use particle P because there's no frictional force involved in there, so I've got less information to deal with. So let me draw a diagram for just particle P. So forces acting on particle P, we've got a weight of 0.2 G, because the mass was 0.2 kilograms, and we've got a tension going up the slope. Remember, P is the one that's further down. It's being pulled backwards by particle Q. There isn't any friction on particle P because it said it was smooth. Again, let's resolve parallel to the slope. And we'll take down the slope as positive, so we've got 0.2 G sine 45 minus the tension is going to equal mass times acceleration. Well, if the whole system is moving with an acceleration of 3.465, that means particle P must also be moving with that same acceleration, so we can say 3.465 multiplied by the mass, which is 0.2 kilograms. Remember, we've already got this 3.465 calculated to a higher precision in our calculator, so we may as well use that. Rearranging this, we get T equals 0.2 G sine 45 minus 3.465 times 0.2. Remember, for this part, use the answer button in your calculator instead of 3.465 because you'll get your answer to a higher degree of precision. And we get a tension of 0.693 to 3 significant figures. Question 7, part 3. Calculate the speed of the particles at the instant when Q reaches the initial position of P. So Q is going to go down the slope, and when it reaches P it will have travelled 0.5 metres, and we're interested when it's travelled that 0.5 metres, what will its speed be? We'll start by writing down our values for suvat. The displacement, as we've just said, is 0.5 metres. In part 1, at the end it says the particles are released from rest, so we know that the initial velocity is 0. The final velocity is what we're interested in finding. The acceleration we found out in the last question was 3.465 given to 4 significant figures. And we don't know the time. So we're looking to find V in an equation that involves S, U, V and A. The equation we want is V squared equals U squared plus 2AS. V squared is our unknown. U squared is 0, so we can ignore that. So we've got two lots of 3.465 multiplied by 0.5. Now ideally we would want the exact value for this 3.465 bit in our calculator, but unfortunately in the last question we did another calculation since that, so it won't be stored directly as the answer button in our calculator. Now we could work around that, but we don't actually need to, because if you look at this calculation we're doing 2 times 0.5, which is 1, so we're only going to times this by 1, which means we won't affect the level of accuracy. So we can say that V squared to 3 significant figures is 3.465. So to find V, we'll just need to square root that. Which gives us 1.86 to 3 significant figures. Question 7, part 4. At the instant where Q reaches the initial position of P, Q becomes detached from the string and the two particles travel independently to the foot of the plane. We need to show that Q descends at constant speed and calculate the time interval between the arrival of P and the arrival of Q at the foot of the plane. To show that Q descends at constant speed, we're first going to just consider Q on its own. And I think it would be helpful to draw a diagram. So let's think about what we know. Q has a mass of 0.2 kilograms, and we know if it's travelled from Q to P on the slope here, it's going to be 3 meters from the foot of the slope. Let's think about the forces that will be acting on Q. We have a weight downwards of 0.2 G newtons. We have a limiting friction force which we found in the first part of the question. So we found F lim here, and all that depended on was the value of the normal contact force, which only depended on the weight of the particle. This tension here didn't affect that, so in our question we are still going to have the same value of limiting friction, which is 1.386 newtons, or we could use a more exact value of 0.2 G cos 45. So we have F lim equals 1.386 newtons. In brackets underneath I'm going to put 0.2 G cos 45, because if I do a calculation with this I'm going to use the exact value to keep the accuracy of my answer as high as possible. We know the angle is 45 degrees. So we know all of the forces acting on the block, and we know the mass of the block, which means we have enough information to work out the acceleration of the block. Let's think about resolving parallel to the slope. Let's take downwards to be positive, so we've got a component of the weight which will be 0.2 G sine 45. We've got limiting friction going in the other direction, that's going to be negative then, and I'm going to use the exact value, so 0.2 G cos 45, and that's going to equal mass times acceleration, so 0.2 A. Let's factorise this to make it a little bit easier to deal with. So we'll get 0.2g and we'll have sine 45 minus cos 45 equals 0.2a. Once we've done that, we can see clearly that we can do a bit of cancelling with this 0.2. So we get g sine 45 minus cos 45 equals a. So in a bracket here we've got sine 45 minus cos 45. Now if you know your exact values for trig well enough, you'll know that this bracket is going to equal 0. I'll just show you that on the calculator anyway. Sine 45 minus cos 45 is going to give 0. So if you'd not spotted it, it wouldn't matter. So the acceleration is 0 meters per second squared. So because a is 0, we can therefore say that q descends at constant speed. So that's the first part of the question done. We now need to calculate the time interval between the arrival of P and the arrival of Q at the foot of the plane. Let's continue with Q first and see when that will reach the bottom of the slope. So we'll write down some values for suvat. Well, remember it needs to travel 3 more meters down the slope. Our initial velocity is going to be the final velocity from the previous part of the question, because in part 3 we worked out the speed that Q will be travelling when it reached this position here, 3 meters from the bottom of the slope, which is now where we're starting from. So we can say this is 1.86 meters per second. We're not interested in the final velocity. We know the acceleration is 0. And we're trying to find the value of the time when it reaches the bottom of the slope. So we're looking for an equation that involves s, u, a and t. And we could use s equals ut plus half at squared. And because a is 0, that means this term will cancel out, which means we're left with s equals ut, which is a little bit like distance equals velocity times time that you used at GCSE. We're trying to find t, so we're going to do the displacement divided by the initial velocity, which is 3 over 1.86. It's going to give us 1.61 to 3 significant figures. There's no point in keeping any level of accuracy more than that because we've already rounded this value for initial velocity here. It would have been nice to use an exact value for this, but unfortunately in earlier parts of the question we don't have any more precision than 3 significant figures, so that will have to do for now. So we know the time it takes Q to travel 3 meters down the slope here is 1.61 seconds. Now let's consider particle P. And I'm going to draw a separate diagram for this. So earlier in the question we know that both particles have travelled down the slope and Q is now where P is. But because the particles were still attached during that part of the journey, P will also be another 0.5 meters down the slope. So P is going to be 2.5 meters from the foot of the slope at the beginning of this journey here. So we can say this distance here is 2.5 meters. We know it's got a mass of 0.2 kilograms. Remember from right back in part 1 it said the contact between P and the plane is smooth, so there's going to be no friction acting on P. So unlike in the last part, we don't have an F limb going up here. All we have is a weight going downwards of 0.2 g. So if we resolve parallel to the slope, we are going to get 0.2 g sine 45. Remember this angle down here was 45 degrees from earlier. And that's going to give us mass times acceleration, which is 0.2 a. So a is going to be, let's cancel the 0.2 so we don't have to worry about them, g sine 45. Let's leave that as it is because it's simple enough to put in our calculator later. We're not actually interested in finding the acceleration, we're just interested in finding the time at the bottom of the slope. So let's think about our values for SUVAT. Particle P only has to travel 2.5 meters down the slope. Its initial velocity is going to be 1.86 again, because back when we figured out 1.86 here, this was right at the point where the particles became detached. So at this specific point was the last time that both particles will be travelling at the same speed. So our initial velocity is 1.86 meters per second. We're not interested in our final velocity. Our acceleration is g sine 45 meters per second squared, and the time is what we're trying to find. So once again, we can use s equals ut plus half at squared. So our value for s is 2.5. We're going to get 1.86 t plus a half multiplied by g sine 45 t squared. So let's rearrange this so we get a quadratic that equals 0. We get 0 equals a half g sine 45 t squared plus 1.86 t minus 2.5. This is just a normal quadratic with difficult coefficients to deal with, but we can still use the quadratic formula, and we can say that t equals minus b, which will be minus 1.86, plus or minus the square root of b squared, which is going to be 1.86 squared, minus 4 lots of a times c. Because c is negative, I'm just going to write a plus here to start with, because it's going to end up adding this on. So we're going to get 4 lots of a half g sine 45 multiplied by 2.5. Remember, I've already taken the minus sign out here. And we're going to divide the whole thing by 2 lots of half g sine 45. So let's think about solving this using our calculator. If you think about our values of t, they're going to have to be positive. So if we did minus 1.86 minus this and then divided by this, we'd end up with a negative value for t. So I'm not interested in the solution where we're taking it away. I'm just going to do the solution where we're adding this, and I think that we'll get a positive answer for this. So it's essential when you're doing a question like this that you've got a decent calculator, or you're going to really struggle. And we get 0.622 to 3 significant figures. Now when you're doing a long calculation like this, it's probably a good idea to check your answer more than once on your calculator. However, we've got one thing left to do now, because this is just the time when it reaches the bottom of the slope. We are interested in the time interval between the arrival of P and the arrival of Q. Well, if Q arrives at this time and Q arrives at 1.61 seconds, then the time interval will be 1.61 minus 0.622, which gives us 0.988 to 3 significant figures. Okay, that's the end of this paper. Thank you for watching. I hope you find it useful. If you want to find any other past papers